let's see. Density matrix and so this. Which profile? Anyway, QC and Y. Okay, so any question from this time? This time was quite a long time ago, but we go over the review of this time. We go over this teleportation protocol, and we start talking about density matrix. And today we'll be mostly talking about density matrix. A lot of properties about the density matrices. Okay. So the density matrices or density operators are a more general description of quantum states. So we start with this motivation that we want to consider a classical mixture of quantum states. So at the pretty beginning of the course, we said the quantum states are those vectors. So they are those complex vectors in some Hilbert space. And basically finite dimensional space for them. So they are vectors. But now we want to think about classical mixture of them, and that cannot be quantum superposition as we see this example. So we have this example of plus state getting measured and in computational basis, and it becomes 50% 0, 50% 1. And if we kind of cover up the measurement result, and we don't know which 50% we got, then we got like this probability mixture of 0 state and 1 state. And obviously we can describe it in this way, but we want a more elegant description, and that's how we get a density matrix. And why we say density matrix? Because it's a matrix just like those k vectors. We think as a vector, as a column vector, and I really should have an example here. So for example, if we have, so how does the matrix and the vector correspond to? So remember, this 0 vector equal to, we think it as a 1, 0 vector. And so if we have like 100% of this 0 state, and then we say the density matrix we want to define is probability times this Kate-Bra matrix. So what's this Kate-Bra matrix? So 100% of the probability. Then, so if we have this example, then we have probability being 1, so it's just 1. And then the Kate vector, as we say, is this vector 1, 0. And the Bra vector is become a row vector, and this is 1, 0. And is this matrix, okay? 1, 0, 0, 0. Okay. And yeah. It should actually, it's a little annoying. So maybe I should write one more line. So we have P1 times this 0 Kate, 0 Bra, equal to 1 times 1, 0, 1, 0. And this is called the outer product. And so don't confuse with inner product. Inner product is like 0, 0, and it's just equal to 1. And the outer product is actually a 2 by 2 matrix, and it's 1 and 1, 0, 0, 0. Okay? So here is the example. And as we do derivation here, we say that if you have a probability mixture of 2 of them, then you want this weighted sum. So maybe it's 1/2 here, and then you will add up with another matrix, etc. Okay. And I guess we have an example down the way, pretty down. Okay. So here we have another example. So the example we have after measurement. So we have 50% 0 and 50% 1. Then the matrix is 1/2 of a 0, 0 matrix, and 0 K 0 bra, and this one is 1, 0, 0, 0, and this one is 0, 0, 0, 1. And and if we add 50%, 50%, it is 1/2, 1/2. Okay, so that's an example of density matrix. And so we start with saying that, well, this density matrix, this will describe the ensemble of quantum states. So if we describe ensemble of quantum state as these pairs of some pure state and some probability. So it's a probability mixture of some pure states. And then we can always write down, well, mathematically write down this density operator. That's just summation of this projector onto the states, and so they are matrices just like this one. And then we just do an average of them. So we do the weighted sum weighted by the probabilities. So summation I, pi, then projector onto psi I. And so mathematically you can define the density matrix. And we say that the density matrix actually describes everything we know about this ensemble quantum state. So every physical measurement you can do on this ensemble will be described by this rho matrix. And also you can just describe the evolution of this ensemble by doing evolution on this rho. Okay. And yeah, so basically there are two things we need to check. So evolution and measurement. Evolution and measurement. Okay. Evolution and okay, and we are a bit short on time, so let's do this very quickly. And so for evolution, recall that evolution for the quantum state we had before. So those quantum vector state is the psi will get evolved to some u psi, where u is a unitary matrix. And so now you think about how does the ensemble should evolve. Every psi should evolve according to the same u. So it should go every one of them should go to this u psi. Okay? And so you can check that. So if your ensemble going to evolve to this thing, how does this density operator, this very mathematical definition we define here, should evolve? Well, now basically you have all those psi, instead of just psi ket, we have psi ket and psi bra. And psi ket goes to u psi ket, and the psi bra should go to psi bra u dagger. Because, yeah, that's, because it should be a dagger of u psi. Right? That's a dagger of u psi. And yeah, so you see that instead of just adding a u in front, you also add a u dagger at the end, because you want to also evolve this psi bra. Okay. And yeah, that's exactly what we get. You can do the linearity and pull things all inside this u and u dagger, and see that rho will get evolved to u rho u dagger. Okay, so so we see that. So here, since that we do nothing but we do a little proof, we prove that we can write the corresponding. So here we write the corresponding density matrix for this evolved ensemble, and we see that we can describe this evolved ensemble by just doing calculation on the original rho. Okay. So we can describe the evolved rho, which is this thing, by just applying things on the original rho without going into the detail of the ensemble. Okay. So if your ensemble can evolve with u, then you just apply u and u dagger before and after your rho. You don't need to roll all the PIs to know how it evolves. Okay. So that's really cool. And how about measurement? Measurement, and it's also a long calculation. So suppose we do some generalized measurement that's described by the set of measurement operator nn on our example. And okay, it's quite annoying. And we see that we can also describe the measurement outcome by doing calculation on rho. And the short answer is basically we will get a subnormalized state as NM row and dagger. And this is kind of in a similar vein of this, right? Like after, because so is written CF. Like in the previous measurement result, we say we can basically see things by seeing that the measurement outcome as the MM psi, and here is a similar thing. So instead of psi, we have rho. So instead of just doing MM in front, we have MM dagger at the end. Okay. So rho becomes some normalized state. When you measure one count in small m, it becomes the some normalized state m and rho m dagger, and then we can calculate the probability and actual normalized state. And the probability now is a different thing. The probability before was like a non-square of this thing, and the probability now is a trace of this density matrix. This okay. So the probability will just be a trace of the summarized density matrix, and then the actual post-measurement state is this matrix normalized by dividing the probability. So it's this thing here. Okay. So yeah. So guess the the moral of the story here is we prove that this measurement outcome can also be described by rho without going to the details of the ensemble. And let's see, do we have time? We may have a little. Okay, let's go really quickly. And we can also, and here in the actual derivation, we go over all the calculation by going to the ensemble interpretation and see if you calculate everything. So you do a measurement on this ensemble, and you see that the outcome actually just correspond to this thing we described by rho. Okay, so let's read really quickly. So the probability of seeing outcome m, and and you really need to consider. So we consider that what about the probability of each side give you outcome m, and so that's the probability of getting outcome m condition on your input say is I, and well that's as before, that's this as we say it's a non-square of this nm on psi I, and so it's this thing, and so we sandwich non-square of this thing, so it's an inner product with itself, and then we do the trick of seeing that the trace is invariant under cyclic permutation, so we can, so it's the trick we used before. So this is a number, so it's a 1x1 matrix, so we can add a trace. Okay, so now we go to green. We are saying that this number is same as a trace of itself, and then once we have a trace of a whole bunch of matrix multiplying together, so we are also seeing the column vectors, the row vector and the column vectors as matrices, then we can do arbitrary cyclic permutation of them, and it's still the same thing. So we permute this side to end. Okay. So the trace of element dagger and then side column vector, side row vector. Okay. So that's the probability of getting outcome m given the input state is I, and then we want to average over all those probability I. Okay, so the probability actually getting outcome n is sum over I, then is pi, and this is conditional probability, and then you just expand out is this thing, and then you see you look for things that depend on I because you are summing over I. So things depend on I on this sum over pi and this side projector, and so you can pull this summation inside here because everything linear, and then you once again we have this sum pi and the projector on two side, and you see that's rho. Okay. So so you see that all those pi and the psi plus psi ket can be combined together to just depend on rho, and you don't need to know the detail about pi and psi to calculate this probability of outcome. So and we got this trace and dagger and rho, and we can write it in a more symmetric form of doing the cyclic permutation again, moving the n to the end. Okay, question. quadrant, then the outcome probability is a similar thing. So we can see the post-measurement outcome state, post-measurement state of outcome M, and we can check it for every side first. So every side, the post-measurement outcome state should be this thing. So this is a normalized state. And then we calculate. And here is you just plug in the formula of chapter 1. So it is mn psi and divided by normalization. And we see the normalization is p condition on n, pn condition on I. And then we need to do a little probability theory. So the rho n after, so the total density matrix after the measurement, it will be P. Okay, so here is a bit tricky. It should be sum over all possibility I, but it should be Pi condition on M. Because you know your outcome is M, but every side can have different probability or give you M outcome. So now the probability, when you do measurement, some side is easier to get MM. Get the M outcome, and some other I, maybe some other J has a probability lower to get outcome. So this is summation Pi, we should get changed to summation Pi condition outcome is M. Okay. And the outcome state is this thing. And so we have do the conditional probability theory here. So conditional probability is the joint probability divided by So probability. Conditional probability I given by n is the joint probability divided by the probability of given n. Is because we have the I guess we have, forgot how this rule called. But in probability theory we have PIN equal to P. This is derived by probability of getting outcome I, getting both the event I and M is probability of I condition on n times probability of M. And also equal to probability M condition on I and the probability I. This is on probability theory. And so we use both of them. So you see we can express Pi condition on M as this joint probability divided by P of M. And then once again we write the joint probability as Pn condition on I times P of I. Because we have calculated the Pn condition on I before. That's easier to calculate thing. Okay. And and now we all know everything. P of I is up here. And P of n we also calculate here. So now we just need to plug in everything. So rho n is this. So now is a Pi condition on n. We plug in this whole formula. And so we have a Pi from here. And Pn condition on I is going to be cancelled by here. Because the psi m has divided by square root of Pn condition I. And when you take the ket broad, then you have a square here, so you only have a Pn condition I. And finally you have divided by Pn. And and the upper thing is just this thing and the dagger of this thing, so n psi and psi and dagger. And okay. And so now you see the Pn condition I cancel. Once again, the only C condition I is the summation of Pi and psi, ket, psi, and broad. So they just combine into rho. And you see this post-measurement outcome state can be described just by rho. And it's sandwiched by n dagger, then divided by Pn. And Pn, as we say, is this thing. It's just a trace of the upper thing. Okay. So we prove the thing we want to prove. We say the evolution and so the evolved density matrix and the post-measurement outcome density matrix can all be described by the density matrix itself. We don't need to go back to the ensemble interpretation. So question about the proof or the thing we try to prove. Not, then okay, let's keep going. So first some notation thing. So there is a pure state. I think I said this a little before. and but now we already gave definition. So what's pure state? Pure state is a density matrix that can be written as a projector onto some state side. So some side K, side bra. With this, then we call it pure state. Otherwise, we call it mixed state. And so what's pure state is, so pure state is basically what the kind of state we had before. So in terms of ensemble, it's 100% over some K state side. Okay? And yeah, and so we also call this K side as a pure state because it's really kind of interchangeable. Although mathematically this is a matrix and this is a column vector, but we see that we just changing the interpretation, they are equivalent to each other. Okay? Although mathematically they are very different objects, so sometimes it's a little confusing. But I think this is okay abuse of notation. Anyway, so this is a pure state and a mixed state. This is something some notation you should remember. Okay, then let's see the more properties about the mixed states or density matrices. Okay, and so we start with saying density matrices are describing an ensemble of pure states. And but what about ensemble of mixed states? So if we have a probability mixture of a whole bunch of density matrices, what are they? Turns out they are still mixed state, and we have a very easy formula to calculate it. So you have some probability mixture of those rho I, and then the resulting mixture, so it's a little recursive. So we have probability mixture of those rho I, and we say if the rho I is a probability mixture of some pure state, then you see that this is just a bigger probability mixture of all those individual states. And yeah, so it will give you another density matrix. It's just a projector onto all those psi ij probability mixture. And but they actually have easy way to calculate this. As we said, this rho I should describe everything in this ensemble, so we should not need to go into this Pij, Sij. And indeed, we want to calculate the rho correspond to this mixture of mixed state, the Pi mixture of a mixed state rho I, and it's just some Pi rho I. Okay? So it's very easy, you just take basically average of all those rho I. Okay? So yeah, that's pretty cool. Okay, and hopefully this is what you expect. That's the outcome. Okay. Okay. So finally, we go to examples. Although we should have example a little earlier. Yeah. And so the first example is something that we can quite do on a pure state. So we can describe this weird state as you do a measurement onto some density matrix or some state. So this rho might be pure, might be mixed. And then we can do this measurement, but not quite knowing the outcome. Like if you cover up the outcome, and so the state will actually get changed to something else. So it's like what do we do the example here, right? So if you do a computational basis measurement on this plus state, it will get changed to something else. But yeah, and we cover up the measurement results, so you don't quite know the resulting pure state, but the state will definitely get turned to something else. And we can think this something else as a mixed state, as we kind of know right now. Yeah. And so yeah, this is a general thing that we can describe in a method. A very nice form. So the state rho after you do a measurement will be this rho prime. That's a mixture of the state rho and way before, right? And we just plug in the formula. So it should be summation over probability of getting outcome m, and the post-measurement state rho m. And post-measurement state rho m is n rho m dagger normalized by pm. And so you see Pn cancel, and it's actually just summation m rho m dagger. Okay. So it's a summation over all the subnormalized states of getting all kind, and yeah, so you see you have a pretty elegant result. Okay. And once again, remember that this is most of the time not same as the original state. Even though you don't know the measurement outcome, you do a measurement, you will change the state. Is something funny in quantum mechanics, and also this is some description that we don't quite have when we only have pure state, only mixed state. As in pure state, we can say like a probability of getting something, probability of getting something. But now we can describe that in this very succinct form. Well, I guess at least algebraically it looks really clean. Although when you actually write down things, because it's a matrix, so it's like actually n squared element, and yeah, it's actually more annoying to write down sometimes. At least it looks very cool here. Okay, so let's see an example. So finally, our example of plus state measure in computational basis 0 and 1. Okay, so the starting state is this plus ket and plus bar, and remember the plus state is 1 over square root 2 1 1. Okay. And so you do the outer product, you see it's 1 1 column and the 1 1 row become 1 1 1 1, and the 1 over square root 2, there are 2 of them, so it gives you 1 over 2 everywhere. Okay, so starting state is this 1 over 2 1 over 2 1 over 2 1 over 2, and then we do the measurement, and so there are two ways to see this. So you see the pure state in sample interpretation, that you know the output should be 50% probability getting 0 and 50% probability getting 1. And or we can do this calculation or we can do this calculation carefully. So we have this plus density matrix in the middle, and we sandwich with the two measurement operators, right? So first we sandwich with the 0 operator, then we sandwich with the 1 operator, and then you see this inner product between 0 and plus is 1 over square root 2, so 2 of them is 1 over 2, and also the inner product between 1 and the plus is 1 over square root 2 also. So you get 1 over 2 here and 1 over 2 here. Those are numbers, okay, because it's inner products. And then you left with, once again, 0k to 0 bra, so that's the matrix, and 1k to 1 bra, that's the matrix. And yeah, anyway, through different interpretation, you know the output state is 1/2 of the 0 projector plus 1 projector. And so you write down 0 projector, 1 projector, and you see that actually, so it actually, equal to this 1 over 2, 1 over 2 matrix, and it's 1/2 of the identity matrix. Excuse me. It's 1/2 of the identity matrix. Okay. And yeah. So the first thing we want to check is that you see that this matrix is different from this matrix. Okay. So we prove that we can. This plus state you measure in 0, 1 basis. Even though you cover up the measurement result, it will contain into a different state. So it will collapse the state, you don't know what it collapses into, but it already changed the state. Something interesting. And this state is also called totally mixed state and maximally mixed state. Okay. And so totally mixed because kind of it has no bias between 0 and 1. It is 1/2, 1/2. Okay. So it's like mostly the state with the least amount of information or massive amount of information, depending on how you interpret the information. Yeah, and yeah. And but there's a really cool thing about this. I believe you were doing homework. That is actually a totally mixed state. At least we can prove, yeah, we can prove quite easy in 2 dimensions. So this thing actually doesn't depend on basis. Oh, actually it's it's the end of the slide. But Okay. LM style a little more. Okay, so maybe let's just go spoiler here. Okay, so the totally mixed state we say is 1/2 of 0 plus 1/2 of 1. So you can think, once again, remember we have this block sphere on a qubit, and the totally mixed state is 0 plus 1, 1/2, 1/2. And actually is equal to 1/2, 1/2 of any two like symmetric point on this block sphere. So you have 1/2 1/2 of minus plus 1/2 of plus is also a total mixed state, and also y-axis or any axis. Okay. So yeah, so in this sense, it is hiding a lot of information. It doesn't even tell you what basis you are in. Okay. So it's something very cool. So we'll have ID. So homework, and yeah, so 1/2 ID equal to 1/2 of psi plus 1/2 of some perpendicular not in block sphere but in the two-dimensional space, in a Hilbert space. Yeah. So any state and its perpendicular part, if you take the equal mixture of them, you will become the total density matrix. And yeah, so in particular, equal to 1/2 plus plus and minus minus plus 1/2 of minus minus. And this is the basis of a lot of quantum cryptography. So like someone sending random 0, 1 or plus minus, and if you don't know which one he is sending, then you are getting a totally mixed state and you don't really know anything. But then if we review it, and then you can check it whether it's 0, 1 or plus minus with some probability. Okay, and yeah, but that's some digression about this. And you can also see this phenomena, I think, in homework. When we calculate the ensemble or the density matrix of the teleportation state. So now I guess let's go back to teleportation, right? So teleportation, here we have a similar thing happening, and we say the bulb will have like 1/4 state here, and you can calculate the density matrix here, and you see it's a totally mixed state here, and so that really has no information about the thing Alice want to teleport. But then if Alice reveal like which one of 4 it is, then Bob know a lot about the state and can correct the state that Alice want to teleport. Okay. So yeah, this is how a lot of the quantum cryptography works, and it's a really unique quantum information. Okay. And okay, if everything is okay, then let's go to a cool theorem that tells us the characterization of density matrices. And yeah, so before, okay, well, let's talk a little more. So before, what we have right now is we say we got an example of quantum state, and we can calculate density matrix in this form. You have summation pi projected onto size. And okay, so okay. And now we kind of want to go reverse. Then we want to say, what if we just get some density matrix 0? So we get whatever matrix. Then can we know it is corresponding to some example? And yeah. And I have the quadrant because I know the answer is yes. And we have a really easy characterization. So it turns out that a matrix is a valid density matrix if we only need to check these two conditions. So first is that the trace of your matrix is 1, and the second is that your matrix is PSD, positively semi-definite, means that you take a sandwich of it between any vector psi, and it should give you a positive number. Well, obviously your vector cannot be 0 vector. Okay. So you need to check those two things. And then you are a valid density matrix. That means you can always find ensemble corresponding with it, but it's if only if the condition. So that means the ensemble interpretation we had before, they will always satisfy these two, and also you satisfy those two, you can find the corresponding ensemble. So all those states are the set of states. Sorry, I should say set of state. The states that satisfy those two conditions are exactly the set of states that we consider as valid density matrices. Okay. And the first one is like a normalization condition. So before in the pure state case, we said that we consider quantum state and they must be unit state, unit vector. They need to have a known one. And yeah, so the known one condition changed to trace rho equal to 1. Okay. And you can kind of see that it's the same because rho, okay, don't need the red here. Let's do green. Yeah. So they're kind of the same condition because rho is like a psi. And so trace rho, we can do cyclic, and it's like a psi inner product with itself, and that's a known square of your vector, right? Yeah. So those two conditions. Okay, so let's go to the proof of this. And wait, can I? Probably okay. Yeah. So there are two directions. I think the only if direction is a bit easier. So only if direction says that if your rho is in this form, then you must satisfy those two things. So you just need to do proof of calculation. So first, if our rho is come from some example, so our rho is have this form, some pi, psi, and so we just calculate trace. So trace over this thing, and well, it's very linear in everything. So you can just pull the trace inside. So switch order between trace and summation. So you have summation pi, and this part is only the matrix part. So you have a trace. And once again, we do a cyclic thing. So we cyclic here, and we trace a number, and this number is the sign product of itself, and like here. And anyway, this is 1. And trace of 1 is 1, and so you just summation pi, but pi are probabilities, so they should sum to 1, so you get 1. Yeah, so this is a normalization of density matrices. It should trace 1, and yeah, we kind of spoiler it a little bit here, and you see that it makes sense. So when we talk about measurement, we have subnormal state, M and rho, and Dagger. And we say that the probability should equal to its trace, and yeah, now we kind of prove that the trace is normalization, it should equal to 1. This is something you should memorize. When you normalize, the normalization of your density matrix should be trace, and it should equal to 1. And then we check the next thing, so is this actually PSD? So we take an arbitrary vector psi, and and do the sandwich around your rho, and you write down rho. Then once again use linearity. So in summation pi, you can take out outside this, and so you put this. So we kind of see this as a matrix multiplication. Okay, so here it should actually be this thing, right? This side, and yeah. So we can put this psi bra and the psi ket inside the summation of pi, and they just now they multiplies to this psi bra and the psi ket, and now this thing is yeah. Now this thing is just a known square of the inner product between psi and psi and psi ket. So I should say inner product between psi and psi. Okay. And yeah, this is absolute value squared. Because so here we are saying this is a number and this is a number, and this number, so this is actually a dagger of this, and the dagger of number is just a complex conjugate of this. So it's just a known square of this number. And yeah, so non-square of this number, and well, non-square is going to be positive, and positive semi-indefinite, and so the whole thing. So then pi is also positive, so you are summing over the whole boundary of a positive semi-indefinite thing, and it should be greater or equal to 0. Okay, so prove that rho is PSD. Should be pretty easy question. Yeah, and if not, then we go to the other direction, so if direction. And now this is a little tricky. Actually, this is not too hard, but we are being a little picky here. But we're short on time, so I guess we can skip most of the picky part. So here we have a density matrix rho that satisfies trace equal to 1 is PSD, and we want to find the corresponding and we want to find the corresponding ensemble such that rho equal to this form summation pi psi dagger. And it's quite easy to find. You just diagonalize rho. Okay, so skip the first part. So if we diagonalize rho, then we have rho equal to some lambda I psi, and then then we can use the two conditions to see some to get some information about this lambda I. So first we see that the rho is PSD. So then we take if we sandwich rho with each of the psi is greater or equal to 0. So we see all those lambda I are greater or equal to 0. When you sandwich this with lambda, because so here we also use that. We are doing unitary diagonalization, so every eigenvector is also going to each other. Okay, so lambda I is greater or equal to 0, and also then we have a trace rho equal to 1. And when you do trace of this thing, once again you trace, and you can pull inside the trace, and all the psi new product with itself is 1, and so you do trace is just summation over lambda I. And so you see all those lambda I is greater or equal to 0, and the summation lambda I equal to 1. Then lambda I are probabilities, and so so you can just see the lambda I as pi, and all those psi I are your ensemble elements. Okay. So basically you diagonalize your rho, then the eigenvalues are probabilities, and the eigenvectors are your ensemble vectors. Okay, and so that seems simple, but what's the annoying part is we didn't quite prove that rho is diagonalizable, unitary diagonalizable. Okay, so before we only say that so diagonalizable is normal matrices are diagonalizable, and we say Hermitian matrices are diagonalizable, and unitary matrices are diagonalizable. We didn't quite prove that PSD matrices are diagonalizable. So here we are including a page proof of PSD matrices are actually Hermitian and diagonalizable. Okay. So that's a bit annoying. And okay, so 4 minutes, I guess. I guess let's finish this and go to a break. Okay, and really quickly. Sorry. So if we are really picky, then we need to prove that PSD matrix is always diagonalizable. Actually, we also prove that it's Hermitian. And but it's a little unrelated to the quantum. It's more about mathematics. So we are just proving PSD matrix are Hermitian matrix. And well, it's not too hard. So, but we have a cool technique here. So we break the PSD matrix rho into its basically part, real part and Hermitian part. So we want to so it's not P, it's rho. Okay, so we write rho as A plus IB, where A is Hermitian and B is also Hermitian. And how we find AB is you can define the being this way. So A is rho plus rho dagger, and B is rho minus rho dagger, and times minus I. Okay. And so you can check A plus IB. So you have I here, and this minus I cancel. So A plus IB is row Dagger part cancel, you get row plus 0. And also A is Hermitian because you do Dagger, this row and row Dagger switch. And B is also Hermitian because when you do Dagger, these two switch you got minus sign, but also this I give you a minus sign. So B is also Hermitian. So you have the real part of the row and the imaginary part of the row. Okay. And now we have the real part and imaginary part, and then you take the defining equation of PSD matrix. So you take the sandwiching, and you do it on the A part and the B part. And so both of these sandwich should give you some real number, but you have an I here, so this will give you a real number, this give you an imaginary number. But you know the number you got is here real because it's greater or equal to 0. Okay? When we write greater or equal to 0, it means it's a positive real number, there's no imaginary part. So this side B side part should be 0 for every side. And yeah, and that means B equal to 0 because B is Hermitian, we can diagonalize it, and we can do this on every eigenvector of B, and every eigenvalue of B equal to 0. And yeah, so B equal to 0 means row Dagger equal to row, and so row equal to row Dagger, row is Hermitian. And finally, yeah, so that's what we want. Row is Hermitian, and so row is unitary diagonalizable. So we can write row in this form. Okay. So that's a really picky proof of this thing. But the more common part is you just diagonalize it, and then you can find an example corresponding to this density matrix. Okay. Yeah, so I guess it's a good time for a break. So any question? Otherwise, let's have a 10-minute break. Okay, let's have a break. Okay, let's get back to our class. So any question on our derivation or proof of the characterization of density matrix? Once again, density matrix. So we just prove that. So small recap. We start with saying the density matrix correspond to ensemble of pure quantum state. So it's this classical measure of the quantum state, and it's this mathematical matrix that's summation pi psi k psi blah. And we prove that we don't so we are getting rid of the ensemble interpretation more and more. And we say that the evolution and the measurement, you can just look at this row. And actually, you can just see what are valid rows without even having an ensemble in the very beginning. You can just check out where a row has trace equal to 1 and the row is PSD. Then it's a good density matrix. Okay. And yeah. And so now we can write all quantum mechanics instead in terms of row. So we have those three things. We can check what are the valid rows, and we know how row evolve, and we know how row should correspond to measurement. And so we forgot about the ensemble interpretation, and we can describe everything in terms of those density matrix row. And so now we have this rewrite of postulates of quantum mechanics. Okay, remember we have the 3+1 postulate on quantum mechanics, and now we write it. And so postulate 1, every physical system so has a Hilbert space H. And the system is described by a density operator. So this rho density operator or density matrix is an operator. So I call it operator because I kind of think it is something that maps from H to H. And this basically just means it's a matrix. It's a square matrix that has so if this H has dimension d, so this will be a d by d matrix. Okay. So that's why it's called operator, because it makes thing vector from H into vector from H. And the other way we'll write this is we say rho is in this space of a linear operator of H. Okay? And anyway, so the rho will satisfy two things. So it has trace rho equal to 1, and rho is the PSD, and we write it as greater or equal to 0. Means that all the eigenvalues are greater or equal to 0. Okay, and yeah, so here we use the theorem we just proved. So, so the density operators are those matrices of dimension d by d that satisfy trace equal to 1 and being PSD. And then postulate 2, we talk about the evolution, and here is a bit tricky. So here there is something about open and closed system. So this rho description is actually very general. It's the most general thing we can think of, and they even describe open physical system. The system and physical system are interacting with other parts. But the evolution thing we write here is only for the closed physical system. And the closed physical system described by U. Okay. And as we shown before, the evolution you have is rho becomes some rho prime. That's U rho U dagger. So before we have the k vector, we just have a U, but now we also have a product vector in the end, so we need to add this U dagger. And yeah, open system will do something else, and it's out of the scope of the class. Although we already see some example of this that we are going to see, that is postulate 3. So postulate 3, we say that measurement described. So the measurement is described by the same mathematical form. So it's a set of operator, this n dagger, and they need to satisfy this completeness relationship. So summation n dagger times n equal to this identity matrix. And so when you measure a state against this set of measurement operator n, and so there are two things. So there are probability of outcome. Some outcome n is P of n and the trace of n row n dagger. And the post-measurement state is when you get outcome n is still this n row n dagger and normalized by dividing this P of n. So it's n row n dagger divided by trace n row n dagger. So as we said before, you can think the subnormalized state as this n row n dagger. Okay. And then there's yeah, and so we skip a lot of things we said before, but once again, you will get one and only one of the outcomes. So we will learn the m, and then you will learn the m, and the m outcome will happen with probability P of m, and the state will get collapsed into this post-measurement state rho m. And but there is something interesting that we couldn't quite describe before. That is, you can kind of imagine you do measurement and you forgot the measurement outcome, and you can still describe that case, and that's when your rho becomes this rho prime equal to summation m rho m dagger. Okay. And this is actually basically the form of what the state will evolve under open system. But we will not go into detail. We just can look at this for a little bit. Yeah. So you can see there's a little difference. So before you have U and U dagger, before after, and here you have quite arbitrary M and N dagger, and you also summation over this small m. So this is what happened in open system. But anyway, we will not go into detail. This is what we know as we do measurement outcome, and you forgot the outcome. You do a measurement and you forgot outcome, and your state becomes this thing. Okay. And once again, we have the hidden postulate for, where we say that for composite system, the joint density matrix is so if every system has a density matrix rho 1, rho 2 to rho n, then the joint density matrix is this rho 1 tensor rho 2 all the way to tensor rho n. And we have talked about tensor of the matrices, so yeah, so it's a really large matrix. And then yeah, so you still have entanglement. So entanglement for density matrices are actually a bit more complicated, but for now we just say entangled state is state that doesn't equal to rho 1 tensor rho 2 tensor rho n. Okay, density matrix. Or the system that cannot be written this way, but it's quite complicated. Yeah, but we don't go into details. Okay. And okay, we are a bit okay. Then we can finish quite a bit today. Okay, and the next thing. Okay, so next thing is I guess first any question about this new writing of postulate of quantum mechanics? Basically, I think nothing much new is described here. We are just basically compiling everything we have been talking about together here. Okay. So yeah, so we get rid of all the internal interpretation, and we say we can describe all quantum mechanics instead of rows. But I guess some complaint about this is that in practice this is not very nice to use, like when you write proof and things, because well, rho is an object that need more writing to describe, because psi is like when you think about it, so some small complaint about this. So psi is like a d-dimensional vector, right? D-dimensional vector. So like it's about d numbers to describe psi, and but rho is like a d times d-dimensional matrix. D times d-dimensional matrix. And so there are about d squared numbers to describe it, and yeah, so write things in rho usually it's more annoying in notation and things, but anyway, mathematically you can describe these different numbers. Yeah, mathematically you can describe any, or theoretically you can describe everything in terms of a row, even though it might be a little annoying to use. And okay, so the density matrix is really nice. You can write quantum mechanics instead of it. And but now we kind of want to go back to discussing example a little bit. Okay, so this is going back to our characterization of density matrix. So I guess let's jump a little back. So we had before that this if only if relation saying density matrix is valid if only if this. So in particular, the harder part to find is that to prove is that if your density matrix satisfies those two things, and then we say we can find an ensemble corresponding to it, right? We say you can diagonalize it, and it's an ensemble. But actually, this ensemble and the density matrix correspondence is not one-to-one. So actually, there are many ensembles that give you a same density matrix, and in proof here, we just find one of them, the one that's easy to find. And so we already see this example of this, but let's see this once again. So we claim this is true. Okay, and yeah, we claim this is true before, and let's see this in more detail. That's a totally mixed state. So let's see, for example, we have one half being 0 state and one half being 1. This is ensemble, and we calculate that as this 1 half 0 0 0 and 0 0 0 1 half plus 0 0 0 1 half. This is a totally mixed state 1 half 1 half, and also equal mixture between plus state and minus state is also this totally mixed state, and let's see this in more detail. So the plus state you multiply it out is this 1 half 1 half 1 half 1 half, and the minus state you do the projection on it, and it's basically the same thing, but you got minus sign on the off diagonal, and so you take the probability mixture of them. Then on the diagonal you get 1 half back, and on the off diagonal you get 1 half cancelled by this minus 1 half, so it's just 0. Okay. So yeah, as we claimed before, the equal mixture of 0 and 1 and the equal mixture of plus minus are the same density matrix. So the density matrix and the ensemble correspondence is not actually one-to-one. It's I guess it's many to one. So many different examples can give you the same density matrix. So we want to characterize this a little more. Yeah, and as we said, this is something a bit weird because we say the same density matrix is the same quantum state because they describe everything you know about the quantum mechanics. And so you see here we have this weird example where you feel that these two examples are very different because one of them is in 0-1 basis and one of them is in plus-minus basis. They feel they are very different, but actually by all the things we've done before, they are physically equivalent to each other. Okay, if you don't know which one half it is in. Okay, so it's a little weird, but it's actually useful. And as we'll explain a little bit here, this is the basis of a lot of quantum cryptography. So you can hide the information by sending a random 0-1 or plus-minus state, and you can kind of recover from this no information by saying whether it's 0-1 or whether it's plus-minus. Okay. That's a bit of a digression, but for now, let's learn about how to characterize this relationship. So we know now we have an example of a different example give to the same density matrix, and we want to learn that what are those examples that actually what are set of all examples that give you the same density matrix. And so we have the theorem here. This is the unitary freedom of example of quantum state. Yeah. And yeah, so we have a very strict characterization here once again. So So we have that two ensemble P described by Pi psi and Qj psi j. We say they have the tendency matrix if only if the following following condition hold. And before describing the following condition, so we have some definition we stick in here, okay? And that's we make that's the notation that we make describing the density matrix a little easier. So we have the P and the psi here, but actually we can kind of absorb the P into psi by describing those psi tilde as square root of Pi times psi I. Okay. And why we want to do this is because then the density matrix, so the density matrix corresponds to this, then we have a rho equal to just summation I psi tilde. Right? So this is just something that help us simplify the notation because we absorb the P into those psi tilde. Remember before we have summation Pi and psi I. And then we break a P equals square root P and absorb it into the psi tilde. So we renormalize the psi tilde with the associated Pi. Okay. So with this notation, so back to what we're trying to describe. We want to describe whether those two ensembles have the tendency matrix. And we say they have the tendency matrix if only if all those psi tilde is related to those phi j tilde in a nice way. So we say they are. Have the tendency matrix if you can find this nice unitary matrix. Okay. So here the unitary actually being important. The unitary matrix such that psi tilde equal to basically a unitary transformation on those phi j tilde. So psi tilde every I equal to summation j uij phi j tilde. Okay, and yeah, so this is simple, but it's actually a bit weird. Let's see an example. So example we just had it before. So our one have 0 and 0 1 and one have plus minus, and so the corresponding tilde state should be this normalized state. So 1 over square root of 0. And 1 over square root 1, then the rest is 1 over square root plus and 1 over square root minus. And so let's see, can we write every psi tilde as this unitary transform from phi j tilde? So 1 over square root of 0 is 0 is like a plus minus, and so you write down, then you see 1 over square root 0 is 1 over square root 2 of this, and 1 over square root plus 1 over square root that, and 1 over square root of 1 is proportional to plus minus minus, plus state minus the minus state, and the coefficient 1 over square root 2, 1 over square root 2. Okay, and yeah, so you compare those things to the equation here. So then you see, so those are the psi j tilde part, and the coefficient uij are those 1 over square root 2. The first 1 over square root 2 we had here. Okay, so this is basically u11, u12, u21, u22, and so our u is this 1 over square root 2, 1, 1, 1 minus 1, and it's a head-on matrix, and we know it's a unitary matrix. Yeah, so any question on this example? I feel this. Yeah. This is not intuitive, not too intuitive, but this is what it is. And if there is no question, then let's go to the proof. But as we are short on time, the proof will skip a lot of the detail. Okay. I guess the proof has a two direction. One of them is easy. Another one is not too hard but very annoying. Okay, so let's go to the easy direction of the proof first. Easy direction is if you psi and phi satisfy those two relationship, and we can show they have the tendency matrix, and this is very easy. because you just do direct calculation. So psi tilde equal to uij some j uij phi j tilde for some u. And so we can calculate the two density matrix. So density matrix related to psi. The density matrix related to psi, as we say, is just this summation of projector onto psi tilde. Okay. And then we just break this into phi j tilde and see what happens. So now we have a lot of summation. Okay, so we have a summation I we had before, and this psi tilde break into a summation into j, and the other so this psi tilde kit break into summation over j, and psi tilde bra also break into another summation, and we need to change the index, so it is into summation over k, and yeah, so. The first one we have uij and psi j tilde, and the second one you have phi k tilde and uik dagger. Excuse me, uik star. Okay, because this u is a number. Yeah. So number and you do dagger, then it's just a complex conjugate. And then we do a thing that usually do in a proof, that you change the order of summation. Okay, so you have summation ijk here, then you do summation of I first. So you try to resolve the summation of I first. And the only C dependent on I is this uik and uij and uik star. And so you have summation uik and uik star. And what is this thing? This should actually become a delta function, because we say u is unitary. And although we didn't quite prove this, so uij and uik. So if you are fixing some j and k, this uik and uij and uik are actually elements in the jth column. Oh, what happened? Sorry. So it's an element of the jth column of u and the elements of the jth column of k. Sorry, element of the jth column of u and the element of the kth column of u. Okay. And when you do this summation I, then you are going through the element and you are multiplying together with the complex conjugate. So you are actually doing the inner product between those two columns. Okay, so this is the inner product between columns, and you have the star here because we are doing complex number inner product. So one of them need to take a complex conjugate. So this is the inner product between two columns of a unitary matrix, and I forgot maybe we didn't say this, but the property of a unitary matrix is that all the columns of it is also normal to each other. And so we take inner product, and those two columns are also normal to each other. So this delta function is only equal to 1 if only if j equal to k. So it's delta jk. And yeah, then it's delta jk. Then you can break the delta function. So you sum over k, then you eliminate delta jk and turn k equal to j. So it's just summation psi j tilde psi j tilde. And as they said before, this is just rho phi. Okay. And yeah, so you see that rho psi equal to rho phi. Any question? That's the easy part. So use the orthogonal property of the colors of a unitary matrix here. If not, then let's go to the annoying part. But I don't want to go to the detail of annoying part, so let's tell you why it's very annoying here. Okay, the details you can check here. I do this very carefully on the lecture note. Okay. So why is this very annoying? Is because a lot of dimension doesn't match. So here we have a unitary matrix here. So we write this theorem here and we say it's a unitary matrix, and it's very nice, right? But actually, And you see the endpoint, and you see everything is like you have two vector here, two vector here, and it's two-dimensional vector space. It's very nice. But actually, those two doesn't need to be equal to each other. Okay. So what's annoying is that the number of vector here and the number of vector here and the dimension of the Hilbert space, they can be all different to each other. Okay. And so it's really arbitrary. When we talk about ensemble, it doesn't need to equal to a dimensional Hilbert space. You can have any number of vector here, any number of vector here. Like even in the two-dimensional space, you can think about ensemble of 100 vector here and example of 1000 vector here. Okay. So yeah, that's very annoying because you get a lot of useless singular dimensions. Okay. So like when you write this Uij, then you are basically need to pay a lot of the zero vector to make this Uij matrix even make sense, because unitary matrix is a square matrix, but the number here is different from the number here, so you need to pay the level zero vector, etc. Okay, so a lot of proof is dealing with the dimension of those three things doesn't match, and a lot of eigenvector can be zero, and or a lot of vectors are actually zero vector and it doesn't matter, and you get you pay the arbitrary vector to make this here. So, so instead of a unitary matrix here, you might have like a symmetry that are basically vectors with columns that all second to each other. Then you fill it up to a full unitary matrix, etc. Okay. So yeah. So a lot of proof is dealing with the detail, and it's really annoying and not too, although I think it's important in some sense, but since we are short on time, we will skip most of it and let's go to the high level idea of the proof. Okay, so the high level idea is that, well, you have those two density matrices equal to each other. Okay. So you have the side density matrix and the row density matrix, they equal to each other, and that's called our density matrix A. And we'll, okay, so here you see we already do some appending here. So we already appending some zero vectors so that n equal to n. Okay, and anyway, so we have the density matrix A here, and we know it's a density matrix, so we can diagonalize it, because it's PSD and the things. Okay. So we diagonalize A equal to this summation K, and the eigenvectors of A and the eigenvalue lambda. Okay. And then we can use the tilde notation once again to make things a lot easier for us. So A equal to the summation K, K tilde, and K tilde. And then we need to deal with the other edge case of lambda being 0. Let's skip that. And anyway, so so A equal to this thing, and then now we try to express everything instead of those K tilde. Okay. And yeah, it's annoying because lambda K might be 0, but it can be dealt with. And anyway. So we can brute force write down psi tilde equal to, well, some linear combination of K tilde, because we know, well, at least we know the K are also normal basis. So we can kind of write everything. So K is also normal basis. So K tilde is not normal anymore, but K tilde is also orthogonal basis. Okay. So we write every psi tilde as a linear combination of K tilde. That should be possible. And so psi tilde equals summation K Cik K tilde for some Cik unknown. And then finally we start using back to this K tilde density matrix equal to this psi tilde density matrix. And with this expression of psi I. Okay, so summation k tilde equal to this summation. So you break psi equal to the summation of k tilde. And once again, from before and after, so the k part and the broad part, you need to have different dummy variable. So this part break into summation k, and this broad part break into summation l. Okay. So CIK and CIL star. Okay. And then you can see this is summation I of the CIK, CIL star of K tilde, L tilde. Okay. And now you compare these two parts. Okay. You have summation K tilde, Q tilde, so you compare those two parts, summation K tilde, Q tilde, and summation ZC. And this is very similar before, and we see that if this part is delta KO, then those two things should equal to each other. And we can actually prove that that's the only possible case. Basically because all those K tilde is orthogonal to each other. So you cannot have L not equal to K, because this is the diagonal matrix, and it should also equal to diagonal matrix. Okay. And yeah. So because tilde, K tilde are orthogonal to each other for every K, so for these two matrices to equal to each other, this summation, this CIK, CIL part must be a delta function. Okay. And if a delta function, then we can think about this C matrix. It has a whole bunch of columns that's orthogonal to each other. And then we extend it, we can get a unitary matrix. So C matrix, because the dimension doesn't fit, is actually not a square matrix, but we can extend to square matrix and kind of ignore the too fine detail about dimension tuning. And anyway, we can get a V matrix, that's basically a C matrix, and we know it's a unitary matrix. Okay. So okay, I forgot this. The important part is we got a unitary matrix V here. And we can write psi tilde as a basically unitary transform from the K tilde. Okay. And similarly, we can write, okay, then we basically finish our proof. So psi tilde is getting from unitary transform K tilde, and phi tilde, you can do same logic, and it's a unitary transform from K tilde with some W. And then we know that psi tilde should be a unitary transform from phi, because with u that's just this, so you can reverse this unit transform with W dagger. So you do U dagger to turn from phi tilde to K tilde, then you do V to get from K tilde to psi tilde. So, and we know the dagger of a unitary matrix is still a unitary matrix, so you just have a U equal to V W dagger, and so you can go from, so the idea is you can go from phi tilde, then to K tilde, then to psi tilde. And this transformation is W dagger, and this transformation is V. So your U is just a V W dagger. Okay. Yeah. Any question? And yeah, and as we said, there are a lot of dealing with the padding and the zero, because the dimension doesn't match, etc. And yeah, that's quite annoying, but I can be dealt with, and they want to check the detail, it's in the proof here. Okay, any question? So I think complete the characterization of density matrix in the example. So once again, let's go back to what I actually proved. We proved that two ensemble of quantum states, they give you a same density matrix if and only if they can be rotated, they are related unitarily, kind of in this way. So all of the set of psi can be given from unitary transformation on those phi j's. Okay. And okay, if there is no question, then let's start another topic. Let's reduce the density matrix. Okay. And let's see. Okay, it's a little annoying, and well, it's a very useful concept, and it's also a way that we'll get a way that will naturally get the density matrix out of describing quantum system. That is, we can use density matrix to describe a subsystem of an entangled state. And I guess a good example is happening here, right? So, so in teleportation, we see that the global state is this, yeah. And so in some step, the global state is this, and we can, so Alice holding 2 qubits and Bob holding 1 qubit. And we can describe the state Bob is in by calculating its density matrix. And the operation we need to do is this reduce density, I guess the partial trace operation. Okay. And the partial trace is how you calculate the reduced density matrix of an entangled state. Okay. Yeah. So idea once again is like in teleportation. So Alice and Bob have some state that might be entangled with each other, and here we're in 4D general. So in the you see that in the teleportation case, the entangled state is a pure state, but in general case, the state might be even in a density matrix. So it's on density matrix that in the linear space of HA tensor linear space of HB, so it sounds in very big. But sometimes it's maybe if it's a pure state, then it's just psi AB, cat psi V bra, and then we can calculate the it's different from the example, but say we can calculate the state A is in by calculate the reduced density matrix of A. So we say writing as this rho A, and it's defined as the trace B on this rho AB. Okay. And so trace B is the partial trace operation. It's an operation that it takes some density matrix on rho AB to some density matrix on rho A. I think I actually wrote this a little wrong. So this is not in L of HA tensor HB. So this is in L of HA tensor HB. I think this is more correct because this is not entangled state. Okay. Anyway, yeah. But hopefully everyone knows the space we are in. Yeah, those are not entangled state. Yeah. And well, we haven't said what's the partial trace operation. And here we have a definition, but it's a bit bad definition. Although I guess it's okay. It's one of the definitions I can use in calculation. Okay. Quite easily. That is, we define it on computational basis, and we just say, then this partial trace is linearity. Okay. And so computational basis state, partial trace basically says that you trace on the B part. And so you get a state, you have IJ, KL, and you do partial trace. Then you become a density matrix on A part, and that's just this A part IJ. And on the B part, it becomes delta KL. So you get something only if K equal to L. And you can see that it is a trace on B because this delta KL is a trace of this KK and L bra. Okay? And yeah, And you can extend this to define this every density matrix by just saying this is bilinear. So if you have a row 1 plus b row 2 on the A register, then it's just is a plus b here, and also similar on the b register you have linearity. And so equivalent definition is you can prove that. So if you have those non-entangled state, then excuse me, then you have this matrix A cat A bra tensor B cat B bra. So A1 cat A1 bra tensor B1 cat B1 cat B2 bra. Then it's just you do partial trace, you are just tracing on the second part, and then you get this A1 A2 matrix here, and then you just get the B2 inner product with B1. So you trace B1 cat B2, and you do cyclic, and you see this is B2 inner product with B1, and yeah, so this is a number, and so it's a number times the matrix on the A part. And so let's see some example. And first is we have a product state. So if your row AB equal to some row A tensor row B, so basically there is no entanglement between A and B, and so you expect that you do partial trace. So basically, then you should just get back to row A because there is no correlation between A part and B part. So this state is basically just saying A has a state row A and B has a state sigma B, and you are just looking them together as a joint system, and you expect the state of A is just row A, and you see the partial trace give you the expectation you have, and so partial trace on B, then you just a row trace on sigma, and you get back to row. And actually, this is something you need to prove from. So if you are very careful, you need to check this, just like this. So this we can derive from just decomposing everything in basis and do linearity. It's a lot of writing and not too interesting. So if you want it, you can check it yourself. And here is similar. Here you can write the sigma, you can just break into conventional basis and check the linearity. And you will see that this trace B is actually doing here is actually just trace sigma, and then here we see that the normalization of density matrix is being useful because trace sigma will equal to 1, and then you get row back. Okay. If your sigma, where sigma is actually a very density matrix is normalized with known 1. Sometimes you do this just as a mathematical calculation and trade, so sigma might not be normalized here. But if we have a very physical state here, so rho A is a very density matrix and sigma B is a very density matrix, then trade sigma will equal to 1, and then we get a row back. Oh, actually I should say rho A, but anyway. And also here we introduce some notation here, so product state. Well, product state is a state that can be written this way, and by our definition is the state that's not the entangled state. And but now things can get quite confusing here because so there is a difference between product state and the entangled state, and but there is also a difference between mixed state and pure state, and they are kind of related. We'll talk about the relation later. But for now, you need to remember product state and pure state are different things. Also, entangled state and mixed state are different things. Although it's kind of there is some relationship between product state, pure state, and entangled state, mixed state. We'll say later. Yeah, but now you can see that we have a product state here that's actually a mixed state. Because a mixed state on A part, mixed state on B part, and it's a mixed state. Okay. Okay, so this is an example of partial trace, and let's see more example of partial trace. Let's go to entangled state between A part and B part, and it's an entangled pure state between AB, and it's our favorite entangled state, total mixed state. Sorry, maximally entangled state. and spoiling the result. Okay, so row AB is beta 0, 0, beta 0, 0. And now you start seeing the writing density matrix is annoying because you don't want to write so beta 0, 0 is just these two terms, square root 2, 0, 0 plus 1, 1. And when you write down density matrix, it has 4 terms here. And it's a lot of writing here. But anyway, so you expand out the writing is 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, and 1, 1, 1, 1. It's a lot of terms. And then here we do, we do the standard calculation here. So we use the very basic definition, the standard basic definition to do our partial trace. And so we want to calculate the reduced density matrix on A. So for the density matrix on A, when our state is maximum entangled between A, B, and the trace B on this row. And so trace B on this thing, and we use linearity 1 by 1. So trace B is linear, so 1/2 can go outside, and then we can do trace B. Once again, it's linear on all the things, so we can do trace B on all of them. Okay. And so you do trace B on all of them, and so the first one become on the B part you do trace, so you have this inner product between 0, 0. Then on the second one you have inner product between 0, 1. Actually I'm writing this a bit wrong, right? Because the cyclic permutation, so although it's the same thing, cyclic permutation, so it's actually between 1, 0. 1, 0, and this is 0, 1. So on the second part you see you have, on the A part you have 0, 1 left over, and on the B part you have inner product between 0, 1, and also these terms similar. So on the A part you have 1, 0, on the B part you have the trace of 1, 0, so it's inner product between 0, 1. And finally on the last part you have A part 1, 1, and the B part you have inner product between 1, 1. And anyway, those two corrections we just have, they doesn't matter too much because inner product between 0k and 1k is 0, and so we are just left with this 0, 0 and 1, 1, and with 1/2 outside. And so we see that our spoiler is correct. We get 1/2 of identity matrix, and we get totally mixed state. Okay. Question. We have 2 minutes. 2 minutes, so maybe I can say a little about another way to do calculation on density matrix. Although, so remember trace. So we have been doing trace by doing the cyclic permutation, right? Because sometimes it's easier. But remember trace, right? Trace, if just on something, trace of some matrix A. If there is no, is a actual trace, not partial trace, is like a summation I, and this is sandwich A with all basis element I, right? Okay, like this is how you get a diagonal element of I. Okay. And so partial trace can be written in similar way. So trace B row AB is equal to, but you are only, so you are doing partial trace. So you are only summing over the basis on the B part. So it's actually summation I, but it's a weird thing, right? So I guess I should write in this way. So this is what we allow. So I tensor. So I on A tensor this I bra on B, then row AB, and I on A, answer k times b. Okay, it's a really weird thing, and yeah. So you can also do partial trace with this kind of form, if this is more familiar with. Sometimes it feels a little more natural, but it's a little weird because you have this not quite a matrix thing. But I think we have defined, we have defined this kind of operation when we define Dirac notation, and so this will cancel all the b part vectors and will give you a partial trace, and you can kind of see it here. So you have identity and identity 0 and identity 0 here, then you are left with this 0 and so your summation of this, so the I can be 0 to 1 in this case, and so 0 will, when you do the summation 0, then you will pick out this because this one is only 1 with 0, 0 on the p part. And when you do summation 1, we'll pick out this because it is only 1 with 1, 1 on the b part. Okay. So that's another way to do partial trace. Any question? Otherwise, we are a little over time, and I think we can stop here. This is how partial trace and reduce density matrix. Okay, so see you next Tuesday. We'll keep catching up on our progression. And we'll have some workout today.我们到底出了哪？我们4有出过吗？4有出，4出了。不是4出了，但是4不是上次的4，对不对？等一下，我们要先把这个切掉。5的话。